Hello everyone, and welcome back to the good stuff we have been doing. So today in this video we're going to investigate Weierstrass factorization theorem. So here we want to express, say, sine of x as an infinite product, which says that sine of x equals to x times the product as n runs from 1 to infinity of 1 minus, say, x squared, then pi squared n squared. Also, we have another interesting result which concerns cosine. So it says cosine of x is equals to the product as n runs from 1 up until infinity of 1 minus 4x squared. Then you have a 2n minus 1, then pi squared. Now these two results are very useful, and as we shall see soon see in the next video, because they are not so useful for integrals. Because let's say you want to evaluate an integral from 0 to infinity of, say, sine of x over x dx, which is the so-called Dirichlet integral. You don't really begin with by trying to express sine x as an infinite product. Rather, you want to express it as a series. But the useful series that we care about, we can only arrive at it by manipulating this so-called infinite product. So how do we achieve this result? Well, to begin with, you notice that Weierstrass factorization theorem says that all rational functions can be expressed as the product of their zeros, in the sense that, let's say, if you have an x squared minus, say, 5x plus 6 being equal 0, you can solve this by looking for by writing this as x squared minus 3x minus 2x plus 6 being equal 0, and then that will be giving you x. You have an x minus 3 minus 2, you have an x minus 3 being equal 0. So you have an x minus 2 and then have an x minus 3 being equal 0. So here you see that we are able to express this. The roots of this are x equals to 2 and x equals to 3. So we can express this to equal x minus 2, x minus 3. That is x minus the root. So we can express sine of x to equals to, let's say, and also sometimes there will be a factor, especially when there are rational roots. Let's say there are 2 over 3 here. Let's say 2 over 3 or 3 over 4 here. You could somehow factor these numbers out and you get, say, some constant k. So you can write sine x as a constant k times the root. First of all, x has to be among, because if you plug in x equals 0, sine of x, sine of 0 becomes 0. So 0 is also a root for the sine. So x belongs, what belongs again is this. You have an x minus, let's call the root r1, and let's call the second root r2, and let's call the third root x minus r3, and so on. So they are infinite, of course. So you have an they're infinite, of course. So let's you could also have an x minus rn, r sub n. Now let's create a little bit of breathing room here at the very top. Let's take out everything and do some demarcation. So now observe one thing here, that you can write this as sine of x to be x times, let's say, we already said this is x minus, say, r1, x minus r sub 2, and x minus r sub 3, and so on. So x minus r sub n. Now the r's are, if you look at the unit circle, the only part that sine of x becomes 0 at either at 0 or at multiples of pi. So you get, first of all, you get an x. Okay, there's a k. So you have a k times an x, and then you have an x minus pi. Although, because even sine pi equals 0, same thing as sine of negative pi equals 0. So the first one, the root will occur in conjugate pairs. So you have an x minus 2 x plus x, not minus 2 pi. You have an x plus pi. So you have an x plus pi, and then also you have an x minus 2 pi, and then you have an x plus 2 pi. The roots occur in conjugate pairs. You also will have an x minus r pi, and you have an x plus r pi, and so on. So if when you put this together, you could factor out the pi. So you have to write k x pi, and then on this side you would have 1. Oh, don't worry about whether it to be a negative or not. The k will absorb the negative sign. So you have a 1 minus x divided by pi. On this side, you have an x plus, so you have a 1 plus x divided by pi. Here you have an x, because you have a 2 pi, so you assume this is a 1 over 2 pi. So you have an x minus 1 minus x over 2 pi rather, and you have a 1 plus x over 2 pi. Then going further, you have an 1 over r pi. So you have a 1 minus x divided by r pi, and you have a 1 plus x divided by r pi. So of course these constants we factored out can all be absorbed by k. So we consider this as k multiplied by, then in this case you have an x, so you have a 1 minus x squared, and then you have a pi squared, and you also have a 1 minus x squared over 2 squared pi squared, and you also have a 1 minus x squared over 3 squared pi squared. So if we continue further, let me erase this. So if you continue further, you would this continues to infinity. So you have sine of x. This means that sine of x is equals to kx times the product as n runs from 1 up until infinity of 1 minus x squared. Then you have an n squared pi squared. Now you can divide by x, so you have sine x divided by x to equal k times the product as n runs from 1 up until infinity of 1 minus x squared over pi squared n squared. Now everything is almost done, except that we need to recognize that we need to find the value of k. Well, notice that if we take the limit as x tends to 0 on the left, so the limit, it is clear or well known that the limit as x tends to 0 of sine of x divided by x equals to 1. On this other hand, if x goes to 0, you still get a 1, because 1 times 1 times 1 times 1 up until whatever will always be a 1. So the both sides will agree. So this forces k to equal 1. So this means that indeed sine of x is equals to x times the product as n runs from 1 up until infinity of 1 minus x squared divided by pi squared n squared. So this is the first of many we are going to derive. So let's put it in a box and let's go to another fresh page and work something out. So now we are on this. So welcome back now. So let's investigate for cosine. Same principle happens. Cosine of x per se can be written by as k. Then you put the product of the roots. So you have an x minus say r1, the first root, and you have an x minus r2. Then you have an x minus r sub 3, and so on. Then let's demarcate this over. Oops, no. I don't know why I can't throw the perfect. Look, I think there's a line here. Okay, something like this should work. Yeah. So better. So you have an x and so on, up x minus, oops, not the line. So x minus r sub n and so on. So the next part is that you know that the root of cosine, if you draw your so-called arrows, you start from 0 to pi and then the 3 pi over 2 and then pi over 2. Cosine only becomes 0 only at this extreme point. So the first root would be k x minus pi over 2. The second one would be, of course, x plus pi over 2, because cosine of negative pi over 2 is same as cosine of pi over 2, which is 0. So the next one here will be x minus 3 pi over 2 and then x plus 3 pi over 2, and then the next one here would be x minus 5 pi over 2, and then you have x plus 5 pi over 2 all to infinity. So you have k multiplied by this one around, you have an x, you have an we could factor out the pi over 2. If we do that, we'll be having a 2x squared. So you have a 2x minus 1 minus 2x over pi. Yes, here we'll be having 1 minus 2x over pi. Let's take this out. So you have 1 minus 2x over pi, and then here you have a 1 minus x over pi rather. 1 plus x over pi. The next one is 3x. 1 minus 3x over pi. Don't worry about the constants we factor out, okay, because everything will be absorbed by k. So you have a 1 minus 5x over pi. No, it's the other way around. Let me take this out. Because let's see the factoring here. So let's say on this first part, you want to factor, you have an x minus pi over 2. So that would be negative pi over 2 minus x. So that would be negative pi over 2, 1 minus x divided by pi over 2. So that would be a negative pi over 2. So you have an x minus 1 minus 2x over pi. Okay, what about the second one? If you want to factor x minus pi over 3, the same thing happen. You end up with negative, the 3 pi over 2 rather. You end up with negative 3 pi over 2 minus x, and if you factor out, you have negative 3 pi over 2, 1 minus 2x over 3 pi. So in this case, the first one is 1 minus 2x over pi, and the next one will be, of course, 1 plus 2x over pi, and the next one will be 1 minus 2x over 3 pi, and the other one will be 1 plus 2x over 3 pi. We will also have 1 minus 2x over 5 pi. The next one will be 1 plus 2x over 5 pi. All of these factors would be absorbed by this k here. Okay, so let's erase this part of the board. So now when all is said and done, you would have something like this. This we call k multiplied by, so you have a 1 minus 4x squared over pi squared, and then you have 1 minus 4x squared over 3 squared pi squared, and then 1 minus 4x squared over 5 squared, pi squared, and so on. So this means that cosine of x is going to be k times the product as n runs from 1 up until infinity of what? 1 minus 4x squared. Then you have a 2n minus 1 squared pi squared. Again, if you plug in x equals to 0, k result to 1. So officially we would have in red cosine of x to be the product as n runs from 1 up until infinity of 1 minus 4x squared divided by 2n minus 1 squared pi squared. Yeah, so that would be what would obtain here. So this now is for the sine and cosine. What about the hyperbolic functions? Let's go to a new page. So in the previous video we discussed about the hyperbolic the trigonometric functions, and we already proven that sine of x per se is x divided by x times as the product as n runs from 1 up until infinity of what? 1 minus x squared pi squared n squared. And also cosine of x is the product as n runs from 1 up until infinity of what? 1 minus 4x squared all divided by 2n minus 1 squared pi squared. So now we want to establish the one for sine and then for cos. Notice that sine x is negative I sine ix, and cos x is cosine of ix. So in this case, if you plug in ix for x, I think what you obtain here, by recognizing the fact that if you recognize the fact that I squared is negative 1, you will obtain that cos x is the product as n runs from 1 up until infinity of 1 plus 4x squared divided by 2n minus 1 squared pi squared. Okay, and then likewise, if you try for ix here, you will get sine x is ix times the product as n runs from 1 to product into infinity of what? 1 plus x squared divided by pi squared n squared. Now if you multiply by negative I, here it becomes 1. So you have with okay, this is sine ix. If you multiply by negative 1, you have that sine x is going to be x times the product as n runs from 1 to infinity of what? 1 plus x squared pi squared n squared. So the only difference for cos is that they have plus, while for the normal trig functions they have a minus. But these are the Weierstrass factorization. So thank you for watching, and in the next video we are going to investigate the series representation. Thank you very much for watching, and please enjoy your day, and bye.